Welcome to the lecture series on mathematical modeling, analysis and applications. In the last lecture, we have discussed about linear discrete model for system of equations, and in this lecture, we will just discuss about discrete time linear edge structured models. And the contents of this lecture includes like a Bernoulli-Lewis-Leslie model, that is BLL model. And in the second, we will just go for like projection matrix, and the third stage we will just define about this Leslie matrix, and in the last section we will just go for jury stability test. So, if we will just go for this edge structured models, this means that if the species involved in modeling are studied after categorizing them in several edge classes, then the model is termed as edge structured. In the last lecture, we have discussed about prey-predator model, where preys are present and predator are present, but we did not consider the edge there itself, since only these tigers are eating this deers and the deer population is just getting declined, or in the second case, if we are just considering like if a deer population is declined, then this tiger population are also get declined. But we do not know when this like the edge that the tigers can give birth the next tiger, or the deer can just give birth to the next deer. But here if you just consider like after how many days or how many years, then the deer will just get fertile and it can produce the deers, or tiger can be fertile and it can produce extra tigers. So, if you just consider these edge structure models, then we can have a clear idea about how we can just generalize this model. Till so far, we have studied 3 models, out of which 2 models, linear cell division and linear prey-predator models, are non-edge structured, because we have not considered the edges of species there. If some species, the amount of reproduction varies greatly with age of individuals, hence they cannot be like formulated using non-edge structured models. So, Fibonacci rabbit model may be considered as an edge model, since we have just considered that like one pair it is just existing, and after like 2 months they are just giving birth of like one pair again, and then they will be like fertile after 2 more months. So, in that structure we can just consider it is like after like 2 months you will have like 2 pairs of rabbit, and after 4 months how many pairs it is just existing. In that we are just considering in that form. And if we will just go for this edge structure models, first the whole population is divided into n edge groups. This means that like if a population edge is like that is above certain edges that they cannot produce also any new pairs there, then we cannot also neglect that type of population group also. So, for that we have to divide like this population into several edge groups, and if you just divide like for any arbitrary number n edge of groups for modeling, then we can just separate birth and death rates in different edge groups based on their like edge structures. And here that is why I have just written this statement: in edge structured models, first the whole population is divided into n edge groups. For modeling, separate birth death rates are considered for each edge groups. And if you just go for like the modeling of a human population growth, then this human reproduction rate is proportional to the age of the individual. So, we will be requiring an edge structured model. Let us divide the human population levels into 5 edge classes suppose. So, suppose x1 is the edge class, or the number of individuals from ages like from 0 to 19 at a particular time level, suppose n, and x2n, that is the number of individuals existing from the age of 20 to 39 at that time level, and x3 of n, suppose the number of individuals from age 40 to 59 at time n level suppose, and x4 is the like number of individuals from age 60 to 79 at that particular level, and x5 is the number of individuals existing from 80 to 99 at time n, and we are just considering that no one survives after age 100. Maybe sometimes we can just find that in like different countries people are surviving after 100 also. That is sometimes we can just consider it is like unnatural. And if we will just consider all these assumptions, this is can be like this assumption could be of course be remedied by considering additional age groups, those who cannot like give birth after this age group. So, we can just also consider, or like this is the age that after that the people will get dies. So, that type of constants we can just consider in this class of models here. So, if you just go for this like mathematical representation of all this age group of this human population, then we can just write first age group as x1, which is existing between the age from 0 to 19 here. If you will just see, sometimes maybe it is 0, we can just consider like f1 x1n, f2 x2n, f3 x3n, f4 x4n, f5 x5n. This means that within this 0 to 19 group, some people they can also fertile, they can also produce the babies. And x2n means those who are like in the age group of from 20 to 39, they are also producing this or they can like give birth to the childrens, and whose age will lies between 0 to 19. So, if you just see this x3, that age group also produce the childrens, and whose age will be lies between like 0 to 19. And similarly, you will have like x5 groups which also produce the babies and which age will lies between 0 to 9. And second group, if you just consider like x2, then this population, if you will just see here, that is just given by G12 x1n here. This means that after 19, those who have survived, they can be come to the age group of x2 here. And I have just written here, Fi denotes the birth rate over a period of 20 years for parents in the ith age class, and Gi plus 1, that is G12 denotes the survival rate for those in the ith age class passing into I plus 1. This means that they have crossed the 19th age and they are belonging to the group age of above the 19th. So, that is why it is just written as G12 x1n. Similarly, those who have crossed like x2 age there, they just they did not die, and after that they are also surviving. They are in the fertile group of like x3 here, that is represented as G23 x2 here. And those who have crossed this x3 age bar, then that can be just coming into x4 age group here. And those who have crossed x4 group batches there, they can just come up to here G45 x4n here. And a single set of parents may be in different age groups. We should attribute half of their offsprings to each in choosing values for Fi here. So, in matrix notation, if you will just write this previous model, which can be represented as xn plus 1, this equals to pxn here. If you will just write all these variables, that is represented as x1, x2, x3, x4 and x5 as the variable, which can be just written as in the form of like xn plus 1, then this complete matrix with taking the coefficients as p here, where this vector x is represented as x1, x2, x3, x4 and 5, and the matrix P is termed as, if you just see here, which takes the coefficients for x1 as f1, f2, f3, f4 and f5, which will be multiplied with x1, x2, x3, x4 and x5 there. And if you just see here, x1 takes the coefficient G12 and the rest are 0 here. Similarly, the next group for x2 here, x3 here, if you just see, this takes the age group of G23 here, rest of the elements are 0. Similarly, if you just see x4, then it takes the age group of G34 and G45 it is existing for like x5 here, if you will just see, and which takes the coefficient as x4 here, this is takes the x3 as here, this is a x2 here, this is as x1 here. So, that is why x5 here does not have any coefficient, so that is just taking as a 0 value. If you will just go for this analysis on projection matrix, the numbers written in matrix P will be obtained from data collection. How many like age groups are existing from 0 to 19 and above 19, how many populations are existing, whatever we have just defined for different age groups, that we can just count in a direct from the data only. And do these numbers have some associated meaning, or they are just some arbitrary numbers? So, that we have to also verify. Well, if we will just go for answer this, we need to perform a proper analysis on the data. Among all FIs, that is which one will have largest magnitude and smallest magnitude. Can Fi have a 0 value also, and the similar questions for Gi I plus 1. Since how many people are surviving like after 19 or after 39, how many people are surviving. So, every possibilities we have to consider when we will just go for or define this model. We might expect F1 to be smaller than F2 because parents of age groups 0 to 19 years may be less reproduction rate than parents belonging to 20 to 39 years age group. Yes, definitely it is true. Some very elder parents might not be capable of reproduction, and this results in 0 value for some of these FIs. And if we will go for further analysis, we had assumed 5 different age groups to model the human population here, and hence we obtained a 5 by 5 projection matrix. If you will just classify this model age groups into like 20 like different age groups, then we will have like a 20 by 20 matrix here. So, if we increase the number of classes, the size of population matrix will also get increased proportionally. For example, if we will consider the length of an age group as 5 years, suppose, since sometimes we can just find that like different populations, like if we are just going for a human, it is different, but if we just go for like another creatures, then we can just find there like this age groups difference will be like very certain to get these reproductions. So, in that class we have to like subdivide this age groups into very small sections. And if the length of an age group is 5 years and the last age is suppose 100 years, then the size of U will be like 20 by 20 here. Whatever the size of the projection matrix, we do not mind, it will have the same structure always. The top row reduce the fecundity information, and subdiagonal shows the rate of survival here, and the rest of the entries will be 0 especially. And this kind of projection matrix is called a Leslie matrix. And if we will just go for analysis on projection or Leslie matrix, so stability we have to go for like a human population model, and it will just entirely depends on the Leslie matrix here. And in the last lecture we have learnt about the stability of the system by finding the eigenvalues of a coefficient matrix. Since we have just considered that the determinant of a minus lambda I, this equals to 0, and sometimes if we are just finding that lambda I, at least one of the lambda I is greater than 1, then the system is unstable, and if all the lambda I's are less than 1, then we are just saying the system is stable there. And if at least one of this lambda I is 1 and the rest of the lambda I's are less than 1, then we are just saying that the system is asymptotically stable there. And if we are just going for the size of Leslie matrix, that the size of this matrix P will decide the degree of a characteristic polynomial to solve. In general, there is no generalized method to solve the polynomial of a highest degree or the degree is greater than 2. Since already we have known that if the system is linear, we can have a solution and 2 terms maybe it is present there. If it is a quadratic equation, then we will have a solution, analytical solution. But if the degree of this polynomial is greater than 2, we do not have any analytical method or exact solution, it is difficult to find thereof, especially we are just going for numerical solution. Then what we have to do now? How can we solve it further? Because without finding the eigenvalues, one cannot tell about the stability of the system and whether there is any other method is existing to analyze the polynomial for higher degrees. So, an American electrical engineer named as Eliyahu Ibrahim Juri gave a concrete method to check the stability of a linear discrete time system, which is known as a Juri's stability test. And in a Juri's stability test, first we have to consider a discrete time linear system as in the form of Zn plus 1, this equals to m Zn suppose, where m is a n by n system of matrix. To find the eigenvalues, we need to determine the determinant of m minus lambda I, this equals to 0, and if we will just write this determinant of m minus lambda I equals to 0, this will just give you a polynomial of degree n there. Suppose the polynomial is in simple form represented as q of lambda here. Since all the eigenvalues are represented in terms of lambda, So that is why we can just write this one as a0 lambda to the power n, and a1 lambda to the power n minus 1, a2 lambda to the power n minus 2, an minus 1 lambda plus an equals to 0. Especially we are just considering a0 is not equals to 0 here. Since if a0 equals to 0, then this polynomial will be reduced to a like a degree of n minus 1, which creates a problem here. Since we will have like n by n system of matrices and each of these variables are like non-zero, so then we cannot find the exact solution of this polynomial equation. To apply the Jury's test, we need to form a table here. To create the same, the procedure is as given below. First, we will just consider that in the first row we will just write all the coefficients of polynomial starting from higher power of lambda, and in the second row write these elements in a reverse order, that is starting from lowest power. If you will just see here that the coefficients of this polynomial, which is started as a0, a1, a2 up to an here, a0, a1, a2, n minus 1, an here. If you will just start writing in a reverse form, then a1 is going to that one, an minus 1, then an minus 2, then finally you can just find a1 in this position and a0 is going to the last position there. For the third row, if we will just multiply the second row by the coefficient of an by a0 and subtract from the first row, then we will have like third row here. And the last term, especially if you will just multiply in that form, then you can just find, since we are just multiplying here an by a0 and subtracted from an there, so then you will have the 0 element in the last entry here. And for the fourth row, write the first n coefficients of the third row again in the reverse form. So if you will just write here the third row representation will be like a0 minus an is multiplied by an by a0, so it will just give you an square by a0. Second, if you will just see here, a1 minus an is multiplied here, so an minus 1 into an by a0. Third element will be a2 minus an2 into an by a0, and the last element, if you will just see, lambda n minus a0 into lambda n by a0, so a0 it will be cancelled, so an minus an, this is just giving you 0 value there. And if you just write in a reverse form except the 0 element, then we will have like this will be the first element here, and next element it will just come in this form here, and here the last element will goes up to as a0 minus an square by a0. And again we will just repeat the procedure till a row with a single entry or single non-zero entry should exist, and if any one of the entries will be negative, so at that position we can just say that the system is unstable. And for a0 greater than 0, if all the coefficients, if we will just consider here in the first column of odd numbered rows are positive, this means that the odd numbered rows, if you will just see 1, then 3, then 5, likewise we can just consider, and if all these odd number rows are positive, if any one of them is 0, then the system is stable here because of the unit magnitude of eigenvalue here. And this is nothing but that is Descartes rule. This is the inverse of Descartes rule, that to find this roots of number of positive roots or negative roots of any polynomial. That is nothing but if you will just consider here as q1 is greater than 0 and minus 1 whole to the power n, q of minus 1 is greater than 0, then all roots of the polynomial lie inside a unit circle. Already we have known this one with center at origin, which is the required condition on eigenvalues for a asymptotically stable system here. If at least one of this a0 is less than 0, then multiply whole polynomial by minus 1 to make it positive, and if any one of the three conditions are not satisfied, then the system is unstable here. So if you will just go for the testing of this Jury's stability condition for a quadratic equation here, then we can just write a quadratic equation as q of lambda as b0 lambda square plus b1 lambda plus b2, this equals to 0. Especially in that case, we have just also mentioned here a0 should be greater than 0 or a0 is not equals to 0. We have just considered in this case as a b0 is greater than 0 here. And first if you will just write all the coefficients, that is in the form of b0, b1 and b2, And in the reverse way, if you just write, that can be written as a B2, B1, B0 here. First, we will just multiply this element by B2 by B0 and subtract from the first row here. So, if you will just do that one, we can just find that the last element is 0, and here we can just write as B0 minus B2 into B2 by B0. So, that is why B2 square by B0 here. Similarly, the third element, if you will just see here, that is B1 minus B1 into B2 by B0. So, this element is written in this form. Again, we will just write in a reverse form here. So, first C1 can be written as B1 minus B1 B2 by B0 here, and then again C0 will come to the position of the second element here. Last element, it will just taken as again we will just consider as the difference by multiplying this one. So, last element it will just come as a 0 here. So, that is why the last element D0 is written as a C0 minus C1 square by C0 here. So, in the fifth step, we are just getting here a single non-zero entered number for D0. Since B0 is greater than 0, especially the condition for stability is C0 greater than 0. Since three conditions we have to consider here, that is 1, 3 and 5 odd numbered rows. So, first condition it is just given B0 is greater than 0. We have to consider that C0 must be greater than 0 and D0 must be greater than 0. So, without loss of generality, we can just say that suppose B0 equals to 1 suppose, then the condition for stability turn out are as, like if you just consider directly B0 as a 1 here, then B0 minus B2 square, it should be like greater than 0 we are just considering here. So, based on that we can just say that B2 is less than 1 and B1 should be less than modulus of 1 plus B2 here. And if we will just go for like a Zurich's test for a polynomial of a degree 3 here, then the cubic polynomial it can be written as like lambda cube plus P1 lambda square plus P2 lambda plus P3, this equals to 0 here. And in this case, if you will just see, the coefficients are written as like 1, P1, P2 and P3 here. And in the reverse form, if you will just write this one, this can be written as a P3, then P2, then P1, then 1 here. Then we will just take the difference by multiplying, suppose P3 minus, you will have like 1 by P3. So, then you can just find that 1 minus P3 into P3. So, it will be like 1 minus P3 square. Similarly, P1 minus P1 P2. So, this one can be written as P2 minus P1 P3. So, in the reverse form, if you just write, this can goes to here, this will goes to here, then this will just go here. And again we will just apply this same multiplication, then we will have like R2 equals to Q1 minus Q3 square by Q1, R3 can be written as Q2 minus Q2 Q3 by Q1, and this one will goes to 0. So, again we will just write this one in a reverse form. So, this is the element and this is the element, and finally if you will just subtract then we can just have the element like S3 equals to this one. Now, we will just consider like odd order elements here, that is 1, 3, 5 and 7. So, in the 7th step only we got a single non-zero number S3 here, and the condition for stability is Q1 is greater than 0 and Q of minus 1 is less than 0 here. And for that we have to consider like Q1, since 1 it is already 1 there. So, Q1 should be greater than 0, R2 should be greater than 0 and S3 should be greater than 0 here. After solving all these conditions, we can obtain that P3 should be less than 1 and absolute value of P1 plus P3 it should be less than absolute value of 1 plus P2, and P2 minus P3 P1 it should be less than absolute value of 1 minus P3 square. So, in this lecture we have discussed about this like edge structure models, and for the edge structure models we have just considered like Bernoulli-Lewis-Leslie model, and how this human population we have just considered to represent this like your Leslie matrix there. Then we have analyzed the projection of this matrix and the Leslie matrix. Then to test the stability we have used Zurich's stability criterion for discrete linear system here. Thank you for listening this lecture.